Now that we have got a sense for what's in our data set, as a simple example to get started, we are going to use this data set to train a classifier that will automatically identify any feature pieces of fruit that might come our way based on the features available to the classifier, such as the object's color, size, and mass. To do this, we will use a popular and easy to understand type of machine learning algorithm known as k-nearest neighbors, or KNN. The k-nearest neighbor algorithms can be used for classification and regression, though here we'll focus for the time being on using it for classification. KNN classifiers are an example of what's called instance-based or memory-based supervised learning. What this means is that instance-based learning methods work by memorizing the labeled examples that they see in the training set, and then they use those memorized examples to classify new objects later. The K in KNN refers to the number of nearest neighbors the classifier will retrieve and use in order to make its prediction. In particular, the KNN algorithm has 3 steps that can be specified. First of all, when given a new previously unseen instance of something to classify, the KNN classifier will look into its set of memorized training examples to find the K examples that have the closest features, and we will talk about the closest features. Second, the classifier will look up the class labels for those K nearest neighbor examples. And then once it's done that, it will combine the labels of examples to make a prediction for the label of the new objects, typically, for example, by using simple majority vote. Let's look at a visual example of a KNN classifier that's based on our fruit data set. So what we have done here is taken our training set and plotted each piece of fruit using 2 of its features, the width and the height. These 2 features together form what is called the feature space of the classifier. And we have shown each data points label using the color shown in the legends. So as you can see, there are 4 different colors here that corresponds to 4 types of fruits. These broad areas of color show how any point given a width and height could be classified according to the one nearest neighbor rule. In other words, I've set k equal to 1. So for example, a data point over here that had a height of 6 centimeters and a width of 9 centimeters would be classified as an apple, because it falls within this red area here that the KNN classifier has decided map 2 objects that are apples based on the dimensions. Or for example, if I saw that the classifier saw a piece of a height of 4 centimeters and width of 7 centimeters, it would be classified as a mandarin orange because it falls within this decision area that assigned to mandarin oranges. So what does it mean to have a one nearest neighbor? Where did it come up with these different class assignments in the first place? Well, let's take a look at the apple example over here. The object that has a height of 6 centimeters and a width of 9 centimeters, if you give the classifier that point, what it will do is search within all the different training examples that it's seen. So it would look at all these points and see which one is closest. So we are looking at the nearest single neighbor. So we are looking at k equal to 1. We are trying to find the one point that's closest to our what's called the query point. So in this case, we can see probably that this point over here is the nearest neighbor of the query point in feature space. Similarly, if we look at the mandarin example over here, the closest training set object to the query point is one of those, probably maybe this point right here. Okay, so that's the nearest neighbor of that query point. So for any query point in the feature space, let's say we are over here in the lemon zone. The nearest neighbor to this query point would be this training set point right here. And because the training set points are labeled, we have the labels for those. In the one nearest neighbor case, the classifier We'll simply assign to the query point the class of the nearest neighbor object. So because the nearest neighbor here is an apple, the query point here will get classified as an apple. If you look at the Mandarin orange point here, the nearest data point is the Mandarin orange. So it will get classified in that region. And if we do that for every possible query point, we get this pattern of class regions. The zones where we transition from one class to another, this line right here is called the decision boundary, because query points that are on one side of the line get mapped to a different class. So because this is a k nearest neighbor classifier, and we are looking at the case where k equal to 1, we can see that the class boundaries here, the decision boundaries. Let's take an example over here. We have a point over here that's an orange, another point that's a lemon here. And we can see that the decision boundary, because it's based on Euclidean distance and we are weighting points equally, that the decision boundary goes exactly at a distance equidistance to these two things. That's exactly halfway between these 2 points. Because if it were any closer to that point, it would be mapped to the orange class. And if it were any closer to the lemon instance over here, it would be mapped as a lemon class. So you can see this pattern for all the decision boundaries here. This line is equidistant to those two nearest points. So this is basically how the k nearest neighbor classifier classifies new instances. So you can imagine with query points where k is larger than 1, we might use a slightly more complicated decision rule. Let's take this example over here. Suppose we have a query point that's in orange and we are doing two nearest neighbors classifiers. So in that case, the two nearest points are these 2 points here. And in cases where k is bigger than 1, we use simple majority rule. We take the class that's most predominant in the labels of the neighbor examples. So in this case, the labels happen to agree they are both. Suppose we have a query point that's orange and we are doing two nearest neighbors classification. So in that case, the two nearest points are those 2 points here. And in cases where k is bigger than 1, we can use simple majority vote. We take the class that's most predominant in the labels of the neighbor examples. So in this case, the labels happen to agree. And more generally, to use the nearest neighbor algorithm, we specify 4 things. First, we need to define what distance means in our feature space, so we know how to properly select the nearby neighbors. In the example that we just showed you with the fruit data set, we use the simple straight line or Euclidean distance to measure the distance between points. Second, we must tell the algorithm how many of these nearest neighbors to use in making a prediction. This must be a number that is at least 1. Third, we may want to give some neighbors more influence on the outcome. For example, we may decide that neighbors that are closer to the new instance that we are trying to classify should have more influence or more words on the final label. Finally, once we have the labels of the k nearby points, we must specify how to combine them to produce a final prediction. Here is a specific example of some typical choice we might make for these 4 things. The most common distance metric and the one that scikit-learn uses by default is the Euclidean no straight line distance. So technically, if you are interested, the Euclidean metric is actually a special case of a more general metric called the Minkowski metric. There is a parameter p that's set to 2 that will give you this And in the notebook, you can actually see it in the actual settings. It's done in terms of Minkowski metric. We might choose to use the 5 nearest neighbors, let's say for our choice of k. And we might specify that there is no special treatment for neighbors that are closer. So we have a uniform weighting. Also, by default, scikit-learn will apply for the fourth criterion a simple majority vote, and it will predict the class with the most representatives among the nearest neighbors. So recall that our task was to correctly classify new incoming objects. In our example case, pieces of fruit. So our newly trained classifier will take a data instance as input and give us a predicted label as output. The first step in Python that we need to take is to load the necessary modules as well as load the dataset into pandas data frame. After we have done that, we can dump out the first few rows using the head method to check the column names and get some examples of the first few instances. Now what I'm doing next here in the notebook is defining a dictionary that takes a numeric fruit label as the input key and returns a value that's a string with the name of the fruit, and this dictionary just makes it easier to convert the output of a classifier prediction to something a person can more easily interpret the name of the fruit in this case. So for this example, we will define a variable capital X that holds the features of our data set without the label. And here I am going to use the mass, width, and height of the fruit as features. So this collection of features is called feature space. We define a second variable, lowercase y, to hold the corresponding labels for the instances in X. Now we can parse X and Y to the train test split function in scikit-learn. Normally, the splitting into training and test sets is done randomly, but for this part, I want to make sure we all get the same results. So we get the results of the train test split function are put into the 4 variables you see on the left. And these are marked as xtrain, xtest, ytrain, and ytest. We are going to be using this x and y variable naming convention throughout the course to refer to data and labels. Once we have our train test split, we then need to create an instance of the classifier object, and in this case, a KNN classifier. And then the set of important parameters, in this case, the number of neighbors to a specific value to be used by the classifier. We then train the classifier by passing in the training set data in xtrain and the labels in ytrain to the classifier's fit method. Now the KNN classifier that we are using in this case is an example of a more general class called an estimator in scikit-learn. So all estimators have a fit method that takes the training data and then changes the state of the classifier or estimator object to essentially enable prediction once the training is finished. In other words, it updates the state of the KNN variable here, which means in the case KNN neighbors, it will memorize this stuff in some kind of internal storage for. And that's really all the way to training the KNN classifier. And the first thing we can do with this newly trained classifier is to see how accurate it's likely to be on some new previously unseen instances. To do this, we can apply the classifier to all the instances in the test set that we have put aside, since these test instances were not explicitly included in the classifier's training. One simple way to assess if the classifier is likely to be good at predicting the label of future previously unseen data instances is to compute the classifier's accuracy on the test set data items. Remember that the KNN classifier did not see any of the fruits in the test set during the training phase. So to do this, we use the score method for the classifier object. This will take the test set points as input and compute the accuracy. The accuracy is defined as the fraction of test set items whose stray label was correctly predicted by the classifier. We can also use our new classifier to classify individual instances of a fruit. In fact, this was our goal in the first place. It was to be able to take individual instances of objects and assign the label. So here, for example, we'll enter the mass, width, and height for a hypothetical piece of fruit that is fairly small. And if we ask the classifier to predict the label using the predict method, we can see the output is that it predicts as an orange. I can then pass the different example, which is maybe a larger, slightly enlarged fruit that has a height that's greater than the width and larger mass. In this case, using the predict method on this instance results in a label that says the classifier thinks this object is a lemon. Now let's use a utility function called plot fruit KNN that's included in the shared utilities module that comes with this. This will produce the colored plots I showed you earlier that we have showed in the decision boundaries. We can then try different values of k for yourself to see what the effect is on the decision boundaries. The uniformed parameter that I pass in here as the last parameter is the weighing method to be used. Here I am passing in the string uniform, which means to treat all neighbors equally when combining their labels. If you like, you can try changing this to the word distance. If you want to try a distance wave method, we can also pass your own function, but we'll leave it to that part later. We can also see how our new classifier behaves for different values of k. So in this series of plots, we can see the different decision boundaries from 1 that are produced as k is varied 1 to 5 to 10. We can see that when k has a small value like 1, the classifier is good at learning the classes for individual points in the training set, but with a decision boundary that is fragmented with a considerable variation. This is because when k equal to 1, the prediction is sensitive to noise, outliers, mislabeled data, and other sources of variation in individual data points. For larger values of k, the areas assigned to different classes are smoother and not as fragmented and more robust to noise in the individual points, but possibly with some mistakes, more mistakes in individual points. This is an example of what's known as the bias variance trade-off, and we'll look at that phenomenon and its implications in more depth in the next part. Given the changes in the classifier's decision boundaries we observe when we change k, the natural question might be how the value of k, how the choice of k affects the accuracy of the classifier. We can plot the accuracy as a function of k very easily using this short snippet curve. We see that indeed larger values of k do lead to worse accuracy for this particular dataset and fixed length single train test split. Keep in mind though, these results are only for this particular training test split. To get more reliable estimate of likely feature accuracy for a particular value of k, we would want to look at results for multiple possible train test splits. We will go into this issue of model selection in the later part. In general, the best choice of the value of k, that is the one that leads to the highest accuracy, can vary greatly depending on the dataset. In general, with the k nearest neighbors, using a larger k suppresses the effects of noisy individual labels, but results in classification boundaries that are less detailed. So we have taken several steps in this ML part, machine learning course so far. We have looked at the dataset, plotted some features. We then took the features and learned how to compute a train test split, use that to train a classifier and use the resulting classifier to make some predictions for new objects.